In 2024, 87% of new cars sold in the world still had an internal combustion engine. Combustion engines are highly profitable to the automobile industry. They are affordable and low constraining to end users. Their production does not need critical materials. They refuel at filling stations that are widely available in the world. As global warming demands solutions that are applicable at a global level, fuel-efficient combustion engines have a major role to play in the future. Not only will they reduce oil consumption on a large scale, they will also make synthetic fuels more competitive. Synthetic fuels can be combined with atmospheric carbon capture to create carbon-neutral, stable and long-life storage for intermittent renewable energy. They also have the benefit that they can be produced in regions where wind and sun are abundant. Synthetic fuels and green electricity are both intended to power future plug-in hybrid cars. This carbon-neutral strategy will meet all customers' needs with limited constraints, minimum new charging infrastructures, and low dependence on critical raw materials. Combined with batteries, synthetic fuels could be used alongside fossil fuels and then completely replace oil by 2050. This strategy could make passenger cars carbon neutral in just 2 or 3 decades while properly managing the economic, strategic, and social consequences of the energy transition. In this context, turbulent jet ignition could play a major role. Turbulent jet ignition, also known as TJI, can significantly improve the fuel efficiency of combustion engines at a very affordable cost. Numerous R&D projects have demonstrated that TJI can potentially reduce the fuel consumption of gasoline passenger cars by 15 to 25%. Such an improvement would be a big step forward. Reducing the fuel consumption of all new petrol cars sold in France by 20% would reduce CO2 emissions by as much as if 28% of new cars sold were fully electric. In Germany, this would be equivalent to selling 55% electric cars. However, up to now, turbulent jet ignition has been applied only to big-bore natural gas engines operating steady-state and to Formula One. TJI provides these applications with a brake thermal efficiency of more than 50%. Why not apply the same strategy to passenger cars? Because existing TJI systems do not provide all the features needed for this application. For instance, turbulent jet ignition makes it difficult to guarantee a quick start at very low temperatures, a rapid warm-up of the engine, and a quick catalyst light-off. TJI also poses problems of combustion stability at idle speed and low loads, and emits excessive noise and vibrations over a large engine operating range. Last but not least, most TJI technologies are lean burn oriented. Lean burn helps to achieve high efficiency, but calls for costly and constraining DeNOx after-treatment systems. This negates the advantages of TJI over diesel, particularly in the very cost-sensitive and demanding context of passenger cars. As an alternative, turbulent jet ignition is to be combined with stoichiometric cooled EGR. This permits using an affordable three-way catalyst to comply with emission regulations. But cooled EGR makes implementation of TJI much more challenging, in most cases nearly impossible. In this context, the Valvijet technology drastically changes the game and provides all features that are indispensable to mass-market TJI passenger cars. In Valvijet, the pre-chamber is separated from the combustion chamber by a check valve, which is returned to its seat by a constant magnetic field. When the check valve opens, it forms a jet emission chamber that is connected to the combustion chamber by jet emission holes. A damping chamber protects the check valve against excessive shocks when opening. Valvijet includes a small electric compressor, which supplies a Valvijet air fuel mixer that is no bigger than a can of soda with air under a 40 bars pressure. The Valvijet mixer prepares a rich, homogeneous and fast-burning air-fuel mixture which is introduced in the vapor state into the Valvijet pre-chamber by a high-flow injector during the compression stroke of the engine. This small amount of air-fuel mixture constitutes the pilot charge. As the Valvijet check valve separates the pre-chamber from the combustion chamber, the 40 bars pressure in the air-fuel circuit is high enough to properly feed the pre-chamber with the injector and low enough to prevent recondensation of the air-fuel mixture. The objective of the pilot charge in the pre-chamber is to deliver the most efficient ignition possible, while the main charge in the combustion chamber is intended to maximize the engine thermal efficiency. To achieve these objectives, the air-fuel ratio, pressure and temperature of the pilot charge are drastically different from those of the main charge. That's why Valvijet prevents the main charge from mixing with the pilot charge. Thanks to the Valvijet check valve, the pilot charge remains pure, highly flammable and protected against auto-ignition, whatever the nature of the main charge. With the Valvijet check valve, the combustion of the pilot charge starts in the pre-chamber at constant volume with no effect on the main charge. When the pressure in the pre-chamber surpasses that in the combustion chamber, strong turbulent jets are emitted in a very short time. This forces the main charge to burn very quickly in the combustion chamber, which prevents knock from occurring. Because the Valvijet check valve separates the pre-chamber from the combustion chamber, the mass of the pilot charge is set independently from that of the main charge. This makes it possible to fine-tune the ignition power of turbulent jets. If the main charge is highly diluted with EGR, a big pilot charge is introduced in the pre-chamber. This produces high ignition power and fast turbulent jets. If, on the other hand, the main charge is free of dilution and very reactive, a small pilot charge is introduced in the pre-chamber. This is finely tuned to get the best compromise between thermal efficiency and noise emissions. Thanks to its innovative check valve and its pilot charge injector, Valvijet delivers ignition power on demand under very precise timing. This leads to ultra-small coefficients of variation in IMEP, most of the time below 1% no matter the engine load and speed, even at lambda 2.5. As Valvijet is a fully autonomous turbulent jet ignition system, it can efficiently ignite any main charge, whether it is diluted with air or cooled, recirculated exhaust gases. With Valvijet, starting an engine at very low temperature no longer poses a problem to TJI. For instance, when cold starting the engine at -30 degrees Celsius, as soon as the ignition is turned on, the electric compressor raises the pressure in the air-fuel mixer up to 5 bars in less than 1 second. 5 bars is the limit for partial recondensation of a lambda 1 air-fuel mixture at -30 degrees Celsius. At this stage, limiting the pressure at 5 bars prevents the fuel mixture from partially recondensing in the Valvijet pilot charge circuit. While the piston compresses the main charge in the engine combustion chamber, the Valvijet injector opens and fills the pre-chamber with homogeneous and fully gaseous lambda 1 air-fuel mixture under a 5 bars pressure. Meanwhile, the pressure in the main chamber surpasses 5 bars. This has no consequence on the pressure in the pre-chamber, which stays below 5 bars. At this pressure, despite the very low temperature of the engine, the pilot charge in the pre-chamber does not recondensate, even partially. It remains entirely gaseous and easily flammable. At the appropriate time, the pilot charge is ignited in the pre-chamber. As a result, turbulent jets are emitted into the main chamber, which deliver ignition power hundreds of times greater than that of a conventional spark plug. The engine starts immediately, despite its very low temperature. As the engine temperature rises up, the pressure in the Valvijet air-fuel mixer also increases while staying always below the air-fuel mixture recondensation limit. The pressure in the air-fuel mixer reaches 40 bars when the engine temperature attains 70 degrees Celsius. With Valvijet, rapid engine warm-up and catalyst light-off is also no longer a problem to TJI. Valvijet permits to significantly retard the combustion of the main charge so as to reduce the engine thermodynamic efficiency and increase exhaust gases' enthalpy. At the start of the engine's compression stroke, the Valvijet check valve being closed, a pre-injection cleans the pre-chamber of any residual burnt gases. The pre-chamber forms a closed space where the composition, pressure and temperature of the pilot charge guarantee its optimum flammability. Then, the main charge in the combustion chamber is compressed by the piston up to the top dead center. Beyond this point, the main charge starts expanding without having been ignited, while the pilot charge is introduced in the pre-chamber. Thanks to the Valvijet check valve, the pilot charge is not affected by the expansion and cooling of the main charge. The low pressure in the pre-chamber prevents the pilot charge from recondensing despite the low engine temperature. Late after the top dead center, since the Valvijet check valve is kept closed by the pressure in the combustion chamber, the pilot charge is ignited in the pre-chamber. The combustion of the pilot charge develops in the pre-chamber at constant volume without risk of flame quenching because of the expansion of the gases in the combustion chamber. When the turbulent jets are finally emitted in the combustion chamber, they deliver a high ignition power and strong local turbulence. This provides the engine with high stability despite the delayed combustion of the main charge and produces minimum unburnt hydrocarbons. Retarded combustion can also reduce turbo lag. From the technology standpoint, Valvijet can integrate in any existing diesel or gasoline engine architecture. It is made of simple parts that are easy to mass produce. The Valvijet pre-chamber is fitted inside an insert made of magnetic stainless steel. The insert is mounted in the cylinder head in place of a vertical injector or a spark plug. A spark plug is screwed in the insert, and the pilot charge injector is positioned horizontally in the engine. The Valvijet injector has a radial gas intake port connected to a gas duct made inside the cylinder head. This permits keeping the air-fuel mixture at engine temperature. The injector is actuated by a solenoid. Because of the very small amount of mixture to be delivered in a very short time, a position sensor guarantees a precise needle lift control and pilot charge flow metering. The Valvijet injector offers an infinite number of needle lift variations, for example in plateau, ballistic, or in any form whatsoever. For instance, a prior scavenging opening eliminates residual burnt gases from the previous cycle, while the phasing of the main lift determines the turbulent energy when sparking and the pilot charge heat release. These strategies are decisive for obtaining the most efficient possible ignition of the pre-chamber in all cases. The Valvijet injector operates up to 7,000 RPM and even beyond. It is reliable, robust, durable, and its long and thin nozzle is inserted in between the intake ports of the engine. The Valvijet check valve weighs less than 1 gram. It is made of hard-coated magnetic tempered steel and can move in an abrasion-resistant friction insert mounted in the copper nozzle. The seat of the check valve is made of hard-coated tempered steel. Every Valvijet subcomponent has been developed on dedicated test beds. Once their operation has been validated on test engines over the entire operational range, they are optimized in size, weight, and cost for mass production. Valvijet has been tested on single-cylinder engines and on a rapid compression machine. Valvijet is developed mainly by Danielson Engineering and the Certam, two companies with great expertise in engines development. Danielson Engineering can adapt Valvijet to any existing engine in only a few months. In the end, Valvijet is a short time to market add-on technology. In a regulatory context that is very restrictive for the automotive industry, Valvijet can significantly reduce CO2 and pollutant emissions from combustion cars in the core market in return for a limited cost and investment.